So AR6 has created this metric called multiple climatic impact drivers and how they are projected to change in all the regions of the world. So they have an interactive map on the IPCC site that you can visit. Basically, the climatic impact drivers are physical climate system conditions, for example, means, events, extremes that affect an element of society or ecosystems. Depending on system tolerance, CIDs and their changes can be detrimental, beneficial, neutral, or a mixture of each across interacting system elements and regions. So how they affect, multiply, compound events, and so on and so forth. The CIDs are grouped into 7 types, which are summarized under the icons in the figure we'll see here. All regions are projected to experience changes in at least 5 climatic impact drivers. Almost all, so 96%, are projected to experience changes in at least 10 CIDs and half in at least 15 CIDs. For many CIDs, there is a wide geographical variation in where they change, and so each region is projected to experience a specific set of CID changes. Each bar in the chart represents a specific geographical set of changes that can be experienced in the Working Group 1 Interactive Atlas, which is here. So I will show that next, but just look at this, and I won't spend too much time on the details. Number of land and coastal regions here, open ocean regions here, with climatic driver impacts is projected to increase or decrease with high confidence with the dark shading or medium confidence when there is light shading. So number of land and coastal regions, so you have a scale here. So you are looking at climatic impact drivers like heat and cold, wet and dry, winds, snow and ice, other, which includes air pollution, weather, atmospheric CO2 at the surface, radiation at the surface. So those are the 3. Coastal and open ocean, right? So this is the number of open ocean regions. So under heat and cold, you have mean sea surface temperature, extreme heat, cold spells, and frost. Wet and dry, of course, will include changes in mean precipitation, river floods, heavy precipitation, and pluvial flood. So rain, rivers, landslide, aridity, hydrological drought, agricultural and ecological drought, and fire weather, right? So these are the climate impact drivers. So the regions will experience almost all of them will experience at least 5 of these changes. 96% will experience about 10, and half of them about 15. So wind include mean wind speed, severe windstorm, tropical cyclones, sand and dust storms, snow, snow and ice. You have snow, glacier and ice sheet, permafrost, lake, river and sea ice, heavy snowfall and ice storm, hail and snow avalanches. Other, as I already mentioned, coastal include relative sea level, so that's land versus ocean, coastal floods, coastal erosion, marine heat waves, ocean acidity. So under extremes, I didn't include marine heat waves. There is now more and more evidence that there are also heat waves in the ocean, and the so-called blob in the northeast Pacific, northwest US, in the Gulf of Alaska is well known now, and it leads to massive impacts on ecosystems, fisheries and so on in this region. So that's a very good example of a marine heat wave. There are also identified marine heat waves in the Indian Ocean and West Pacific and other regions. The impacts of these heat waves is not yet completely quantified, and also depends on the definition of the heat wave and so on and so forth. But as the oceans warm, you would expect that there will be heat waves, but unlike the atmosphere, which is light and has low heat capacity, ocean is heavy, deep and has a high heat capacity, so it's not possible to change the temperatures as rapidly as you would do on land or the atmosphere, so you have to be careful about that. In the open ocean, we have a number of open ocean regions with changes in mean ocean temperature, marine heat wave, ocean acidity, ocean salinity, and changes in dissolved oxygen. So there are various impacts of dissolved oxygen changes, or the so-called deoxygenation. When we did carbon, we mentioned how solubility depends on temperature for gases in the water, and off of the coast of Oregon, for example, changes in oxygen levels or deoxygenation is leading to shifts in species where jellyfish begin to dominate ecosystems because they compete better in certain waters which are not very productive. They are filter feeders which can filter gallons of waters and extract food out of it, and they do better where other fish run away or die because of these climatic impact drivers. Okay, so this is showing the these climatic impact drivers in different regions with high confidence, medium confidence, high confidence of increase or decrease, medium confidence of increase or decrease, lighter shaded envelope legend here. Assessed future changes. Changes refer to a 20 to 30 year period centered around 2050 and or consistent with 2 degrees C global warming compared to a similar period within 1960 to 2014 or 1850 to 1900, depending on the particular climatic driver you are looking at. So you have this is one figure. I chopped it off because it's hard to include it in one slide. So these are the ones that go on top here. So you have to go back and look at this from summary for policymakers in the AR6 report. As I said, I don't want to spend too much time on this, but with various confidence levels we can say that all regions are going to experience changes in at least 5 climatic drivers, and 96% of them are going to experience changes in at least 10 climatic drivers, and half of them are going to experience changes in at least 15 climatic drivers. The final thing from AR6 that I want to point out is that if we look at the cumulative carbon, every ton of CO2 emissions adds to global warming. Global surface temperature increase since 1850 to 1900 average as a function of cumulative CO2 emissions in gigaton CO2 here since 1850, and the warming. Here is the historical global warming. The near linear relationship between cumulative CO2 emissions and global warming for 5 illustrative scenarios until 2050. As I mentioned before, this linear relationship is used to say how much room we have in terms of how much additional CO2 we can emit, and taking the per year number, people convert that into number of years left to save ourselves. But this is not a good idea according to many social scientists, and I happen to agree with that view. There are plenty of uncertainties in the system to convert so easily from warming rates to remaining CO2 and remaining number of years to save ourselves. This is kind of a dangerous narrative. It can be misused and it can be misleading. Okay, so here we are with SSP 1.9 to SSP 5 8.5. And here are the future cumulative CO2 emissions differ across scenarios and determine how much warming we will experience. So we are in the historical cumulative CO2 emissions between 1850 to 2019 here. So that's the same number obviously, and then you add different scenarios. By 2030 SSP 1.9 would get us to 3000 gigatons CO2. Okay, this is the unit we are using. 2.6 would increase it further, 4.5 and 8.5, which is definitely not something we want, would get us to about 4,300 gigatons CO2 accumulated by 2050. and the resulting warming would be several degrees, so it's in the range of 1.5 to 2.5 or so. So obviously 2100 will be much higher, and it's better to focus on these time horizons to plan for negative emissions, energy solutions, etc., etc. So let's leave this here and then close out this chapter by looking at something that is not directly related to climate change or AR6 projections, but it is about looking at how we are converting natural resources irreversibly often into human-made substances, and there is a nice graphics provided by so-called visual capitalist, and I'll run through those just to get a sense of just how much junk we produce and how irreversibly we convert natural resources into these products that we use. Okay.